Welcome, everyone. Today we're going to tackle one of the most important concepts in calculus, the precise definition of limits. Now, I know some of you might be asking, wait, haven't we already been working with limits? And you will be absolutely right. We've been using the intuitive idea that limit as x approaches a of f of x equals to L, which means f of x goes to L as x goes to a, right? So we are saying f of x gets closer and closer to L as x gets closer and closer to a. But today we're going to make this idea mathematically rigorous. Why does this matter? Because in mathematics we need precision to prove theorems and build a solid foundation for everything that follows. So let's start with what we've already understand. Consider a function f of x equals to 2x plus 1. What happens as x approaches 3? So when x equals to 2.99, f of this 2.99 is going to be equal to 5.98. As x is equal to 2.999, f of 2.999 is equal to 5.998, and so on. So we can see that as x gets closer to 3, f of x gets closer to 7. But here's the key question. How close is close enough? This is where we need to introduce two important players in our story, epsilon and delta. Think of them as a challenge and response game. Here's the precise definition. We say limit of f of x as x goes to a equals to L if for every epsilon greater than 0, there exists a delta greater than 0 such that if absolute value of x minus a is greater than 0 but smaller than delta, then absolute value of f of x minus L is smaller than epsilon. Let me translate this into everyday language. Imagine someone challenges you, I want f of x to be within epsilon of L. Your response would be, no problem, just keep x within delta of a, and I guarantee f of x will be within epsilon of L. The key insight is that no matter how small the challenger makes epsilon, meaning that how close they demand f of x to be to L, you can always find an appropriate delta that works. So let me show you that with a graph. Let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we can write limit of f of x as x goes to a equals to L. Keep in mind that a function doesn't need to be defined at that a. So then, if for every epsilon greater than 0, there exists a number delta greater than 0 such that if absolute value of x minus a is less than delta but greater than 0, then absolute value of f of x minus L is less than epsilon. So let's say we have a function or a curve, something like this, just a curve, and this is the point where we want to find the limit. So as x approaches this a, so we will grab some interval delta away from a, so we have a plus and minus delta. So this portion right here, that's my distance of delta. So if we take a minus delta and a plus delta, we are guaranteed to land on L minus epsilon and L plus epsilon. So this portion right here, that's going to be my epsilon. Okay, so no matter how far we are away from that A, there is always this distance epsilon away from L. So this is the intuition. So your solution would be within this range. So now let's recall the some examples of absolute values, equations, and inequalities, how we actually work with those. If we have an example, x absolute value of x minus 2 equals to 3, in this case we have two solutions. X minus 2 is plus or minus 3. So we have x minus 2 equals to negative 3 and x minus 2 equals to positive 3. From here we have x equals to negative 1 and x equals to 5. So on the number line, it would look like this, negative 1 and 5. Now, if we have absolute value of x minus 2 is less than 3, then in this case we have x minus 2 is less than 3 but greater than negative 3. From here we can add 2 to all three sides, and we have negative 3 plus 2 less than x less than 3 plus 2, which makes x to be between negative 1 and 5. And on the number line, we'll have negative 1 and 5 here. So this is going to be this interval of interest. And as you can see, 2 is exactly 3 units away to the left and to the right. And now the last example would be absolute value of x minus 2 is greater than 3. So in this case, you have x minus 2 is greater than 3 or x minus 2 less than negative 3. And on the left side, you have x is greater than 5, and on the other side, you have x is less than negative 1. So on the number line, that's gonna look like the following: negative 1 here, 5 here, and you have solution on the left side of negative 1 and on the right side of positive 5. We will have absolute value of x minus a is less than delta, which means that x minus a is greater than negative delta and smaller than delta. So x would be greater than a minus delta and smaller than a plus delta. For the other side, we have absolute value of f of x minus L is less than epsilon. So from here, we see that f of x minus L is less than epsilon, but greater than negative epsilon. So f of x should be less than L plus epsilon, but greater than L minus epsilon. Exactly the same way that we showed on the graph. So now let me write the steps for solving or proving the limits. First one, preliminary analysis or guessing a value of delta. And second, prove or showing that this delta works. Okay, so now let's look at the example. Let's prove that limit as x approaches 3 of 2x plus 1 equals to 7. So step 1, we need to find delta. Now we write, given epsilon greater than 0, we need to find delta greater than 0 such that if x minus 3 is greater than 0 but smaller than delta, then 2x plus 1 minus 7, absolute value of that, is less than epsilon. So essentially, if absolute value of x minus 3 is less than delta but greater than 0, this is what's given, and we need to prove that this is true. That is the end goal. So for now, to do that, first we need to find what that delta should be or can be. So we'll work with the then statement. Absolute value of 2x plus 1 minus 7 is less than epsilon. Now let's simplify the inside of the absolute value. We have 2x plus 1 minus 7 is going to be negative 6. less than epsilon. Now we can factor out 2. We have 2 times x minus 3 less than epsilon. From here on, we can factor out this 2 out of the absolute value because it's already a positive value, so nothing changes. And the last step, we can divide by 2 to get absolute value of x minus 3 less than epsilon over 2. Now, you see that this x minus 3 is the same as in the if statement. So from here on, what we can do is we can choose our delta to be epsilon over 2. Okay, so now we've chosen our delta. Now it's time for a next step to write a proof. Let epsilon greater than 0 be given. Then choose delta to be epsilon over 2. Now assume absolute value of x minus 3 is greater than 0 but smaller than delta. Then we start building up on this x minus 3 to get to the then statement, which is 2x plus 1 minus 7 less than epsilon. So we need to manipulate this if statement so that we get to this then statement. So what do we need to do? It's a good idea to multiply by 2 all three sides, right? So we have 2 times 0 less than 2 times x minus 3 less than 2 times delta. So now this one's still gonna be 0, so I'll just omit that. And I can put this 2 under the absolute value, so I will have 2 times x minus 3 less than 2 delta. So now I can distribute my 2 and get 2x minus 6 less than 2 delta. So now what I can do, I can present this negative 6 as plus 1 minus 7. So I would have 2x plus 1 minus 7 less than, and now instead of this delta, what I can do is I can substitute it with my epsilon over 2, and I will have 2 times epsilon over 2. And now from here, as you can see, we can just put the parenthesis around 2x plus 1 minus 7, and here we will cancel our 2's, and we are left with just epsilon. And we've proved that if absolute value of x minus 3 is less than delta, then absolute value of f of x minus L, right, is less than epsilon. Therefore, limit as x goes to 3 of 2x plus 1 equals to 7 by the definition of the limits. Next time, we will look at the example using the quadratic functions and other type of functions.